Hi there, and welcome to the online part of our classes. So I decided to record the lecture. I hope that works fine. We will see. So as you know, we were almost done with chapter 8 since we didn't have a class for about 10 days. I will repeat a little bit chapter 8 before we move on. Chapter 8 was about sampling distribution, just to make that difference clear to the stuff that we did in chapter 7. Let me review really quick this example. I did this example in both of my classes, so you should remember that, look into your notes, but this is a good refresher, I think. So the question was here that the foreman of the bottling plant has observed that the amount of soda in each 32-ounce bottle is actually normally distributed random variable with a mean of 32.2. Okay, so I just changed the color because I think it's better visible for you guys in the video. Anyway, so the machine is filling up the bottles with a mean of 32.2 ounces. What's the abbreviation of ounces? And a standard deviation of 0.3 ounces. Now, what we did in chapter 7, with the knowledge of chapter 7, we could answer part A. If I buy one bottle of soda, what's the probability that it has at least the 32 ounces that is announced on the bottle? And the bottle is declared 32 ounces. I know the machine has an average of 32.2, but there is a standard deviation of 0.3. Now, with chapter 8, we can also answer a question like, if a customer buys a 4-pack of the soda, what is the chances that those 4 packs, those 4 bottles, have an average of 32 ounces each in the bottle? And that is sampling distribution. That is the stuff that we discussed in this chapter, versus the previous one. Anyway, okay, so let me correct myself in part B. So that what we're looking for is, we buy a 4-pack, and we want to know what is the chance that the average quantity of the 4 bottles that I bought is at least 32 ounces. That in those 4 bottles, essentially in those 4 bottles together, there is more equal or more than 4 times 32 ounces. Right? If the average is 32 ounces for the 4 bottles, that would be 128 ounces. So essentially, we are looking into the question of what is the chance that if I take a 4 bottle, in those 4 bottles combined, I have 128 ounces or more, which means that the average in each of those 4 bottles is 32 ounces. So let's take a quick look into the answer that we did. So before we look into the answer, let me repeat for you the formulas that we had. When it comes to sampling distribution, the standard deviation of the sampling distribution, x bar was the sampling distribution, was the standard deviation of the population divided by the square root of the sample size. So the larger the sample size, the smaller will be the standard deviation of the sampling distribution. So the way we calculated it, again, we go with the z-score. The z-score works just the same as in chapter 7. The only difference is that in chapter 7 we didn't have this square root of n. But technically in chapter 7, because we would always take 1 unit, our n was 1, so divided by square root of 1 is the same value as sigma. So that's why in chapter 7 this was our formula. And now we use this formula. So it's very simple, the same as before. And getting back to our question, so for part A, again, part A was, what is the chance if I take only 1 bottle, that bottle has 32 ounces or more? So this is essentially the formula that we had in chapter 7. You don't see any divided by square root of n. So that should be easy for you guys to solve. We simply calculate the z-score, plugging in the values. Now, the x that we were looking for was 32 ounces. We know the mean of the population is 32.2. So the machine that is filling up the bottles fills it with an average of 32.2 ounces. Standard deviation is 0.3. We plug in the numbers. We get a z-score of minus 0.67. Now, as you remember, hopefully, the z-score of 0.67 Next step would be to look into the values for the z-score. We look into the table. Before looking into the table, we should look again on the picture on the top. The green area is to the left. So whatever value we see gives us the probability that it is going to be less than the z-score that we calculated. So essentially less than the 32 ounces. Now what we had is minus 0.67. Let's take a closer look. It's gonna be somewhere here. Minus, I'm trying to zoom in more so that you can see it on your displays. Okay, my camera person says it's fine. So minus 0.67. It's minus 0.601, 2, 3, 4, 5, 6, 7. We get a value of 0.2514. So 25.14% is the chance that it's smaller than the z-score, right? So 0.2514. Let's take a look here. And that's exactly what we calculated. We were looking for the probability that it's larger than 32 ounces. But again, it's 25.14 is the probability that it's smaller than 32 ounces. So we must take the counter probability. 1 minus the 25%, so it's a 74.86% chance that we have at least 32 ounces if you take only one bottle. Now, and that is something we could already solve with the knowledge that we had from the previous chapters. This chapter we could also answer the question, hey, what if I take a 4-pack? What is the chances that the average of the 4 bottles is 32 ounces? And for that, essentially we do the same steps. The only difference that we need to take into consideration is that my sigma is now different. It's now the population standard deviation divided by the square root of the sample size. My sample size is 4 because I'm buying 4 bottles. So essentially, I'm using this formula, but this formula is now sigma of x bar and not sigma of x anymore, and we know sigma of x bar is essentially sigma divided by square root of n. So this is essentially, as before, just sigma divided by square root of n. So plugging in those numbers, now the standard deviation of my sample, sample size of 4, is smaller. The sampling distribution has a different standard deviation. And because of that, I get a different z-score. My z-score is minus 1.33. So before it was, I believe, minus 0.67. So it was 0.67 standard deviations to the left. But because we have now a sample size of 4, the distribution looks something like this. So because everything is more centered around the mean, as you can tell, the red one has a standard deviation that is smaller than the green one. I hope you remember that still. The same distance, if the population distribution is the red one, is now not 0.67 standard deviations anymore, but 1.33. Minus 1.33 standard deviations. So it's further to the left. If you look it up again in the table, it gives us a 90.82% probability. So essentially that's how we did it. We did that in the class, so you should remember. So essentially what you need to understand is that as our sample size grows, we have here a sample size of 4. Graphically speaking, the distribution looks different. It gets more and more centered around the true mean of the population as the sample size is greater, which makes sense because the bigger sample size means it contains more information from the population. It becomes less and less likely that we get a value that is far off. As you see, the tails become very thin. Here, when we took only 1 bottle, the chances to be far off was pretty high. If we buy 4 bottles, chances of being far off from the mean of the population becomes smaller. So that's the essence of this chapter. Now, let's do the opening example. In the chapter, the opening example was the dean was of a college was claiming that the average salary would be $800 per week, and standard deviation is 100. So essentially, what we have here is again a situation where they're assuming that it's normally distributed. It's about not the salaries of the students when they graduate, and it says that the average salary is $800. And the standard deviation is now $100. Now, a statistics student did his own research. He asked a couple of 25 people who graduated and asked them what was their salary a year after graduation. Now, he asked 25 people, so we already know that our sample size, it's a sampling distribution, the sample size of 25, and those 25 people reported an average income of $750. Now, based on that knowledge, we want to know how likely or unlikely is it if I ask 25 people, and those 25 people report me an average of $750. So it's a very different situation than if I ask only one student, because that is, of course, more likely. Right? With one student, we can already tell it's half a standard deviations to the left, right? But with 25 students, the situation is very different. So we did that example in the class too, so I do it faster. I hope things have already refreshed in your mind. We are looking for the probability. So given that what the dean says is true, right? We want to know what are the chances that I take a sample, assuming that what he says is true, and my sample becomes as extreme as I got, or even more extreme. So we are testing essentially his hypothesis, and we want to take now, we took a sample, our sample gave us an average salary of 750, a sample size of 25. The question that we are trying to answer here is how likely is it to ask 25 students, and those 25 students make an average income of $750, given that what the dean says is true, that the average income is 800, standard deviation is 100. So let's do the calculation. Again, we use the same formula. The standard deviation of the sampling distribution is, again, as before, sigma divided by square root of n. So the sigma was 100, right? So yes, sigma was 100, sample size was 25, so 100 divided by square root of 25. Now square root of 25 is 5, 100 divided by 5 is 20. So the standard deviation of the sampling distribution is only 20. Standard deviation of the population is 100, if what the dean says is true. Now, plugging in those numbers, we want to again calculate the probability. What are the chances that I ask 25 people and those 25 people report me an income of $750 or less? So, plugging in those numbers here, what I have is 750 minus 800, because that's the mean of the population. This is the sample mean. And we calculated the standard deviation of the sampling distribution, and that is 20. So we have 750 minus 800 is minus 50 divided by 20. That is minus 2.5. So we have to look for the z-score of minus 2.5. So two and a half standard deviations to the left of the mean. And that is pretty extreme. So what happens here is that because we have a sample size that is 25, it makes the graph more extreme centered towards the mean, right? It is pretty unlikely that if you have a sample of 25 people, because it's a larger sample, not like the previous example where we had only a sample size of 4, it's a sample size of 25. It becomes fairly unlikely to be far off, right? Now we are kind of far off If you take into consideration that the sample size is 25, you are exactly 2.5 standard deviations away. If it was only a sample size of 1, it was only half a standard deviation away. But with a sample size of 25, we are 2.5 standard deviations away. Standard deviations. And if you look it up in the z-score, that is extremely unlikely. Chances to be 2.5 standard deviations away is less than 1%, 0.62% to be more accurate. So the dean's claim is not justified. Most likely, that is not true. So as you said, with the knowledge that we gain, we can already do some sort of hypothesis testing here as well. Now, besides hypothesis testing, we can use sampling distribution also for inferences. We can essentially, let's say we came to the conclusion, okay, 800 is probably not correct, what the dean was claiming. So we can also come up with an estimate. So what is actually our estimate that those students earn after getting the degree at that college? Okay, but that is for chapter 9. What we do now is kind of a preparation for that. What you should be aware of is, let's assume that the dean was right. Let's assume the income of the student is indeed between $800 and the standard deviation of $100. If that is the case, what we should know is that with 95% probability, the z must be the sample that I take must be between two values. The value here is minus 1.96 standard deviations to the left of the 800, and the value to the right is plus 1.96 standard deviations to the right of the mean. If you remember, I discussed it with you in the class. So if you look up in the z-score table, we see that minus 1.96 represents essentially 2.5% probability. And let me show it to you here. And plus 1.96 standard deviations would be accordingly, let's take a look, minus 1.96 would be exactly minus 2.5, so 2.5%. So that's the most extreme 2.5% tail to the left that we are cutting off. And accordingly, plus 1.96 standard deviations would be 97.5%, which means the green area is 97.5%, right? So if this area is 97.5%, it means this area is 2.5%. So essentially, minus 1.96 standard deviations all the way to plus 1.96 standard deviations from the mean. That means 95% must be between these two values. So, in other words, we calculated the standard deviation of the sampling mean. It was sigma divided by square root of n, and that was 100 divided by square root of 25, which was essentially 20. So 20 is one standard deviation. So minus 1.96 times 20, so minus 1.96 standard deviations means minus 1.96 times 20, which is in this case minus 39.2, and plus 1.96 standard deviations, if I have a sample size of 25, would be plus 1.96 multiplied by 20, which is plus 39.2. So if I take the value of 800, subtract 39.2 from it, which would be 760.8, and add 39.2 to it, which would be 839.2. These are for me the boundaries. In other words, if I take a sample size, a sample of 25 students, and ask them what is their income, if the claim of the dean was correct, and indeed the average income was 800, standard deviation was 100, in 95% of the cases, I will get a value that is between 760.8 and 839.2. In 95% of the cases, I should get a value between those two. This is just something to prepare you for next chapter. If you don't 100% understand it, you don't need to panic yet. Next chapter we will discuss it a little bit more in depth. Now, last part of this chapter is sampling distribution of proportion. If you think back of what we did in a few chapters ago, when we did binomial distributions, all right, so we can use sampling distributions also for proportions. If you remember in chapter 6, I believe, or so, three chapters ago, we did the binomial distributions where you had either 0 or 1. So for example, you toss a coin and you have either head or tail, or where you would go and ask voters, and voters would be either, for example, Democrat or not Democrat. So we were dealing essentially with proportions of success. We can use sampling distribution for those cases as well, even though those cases are not continuous. Here is the formula that we're dealing with. So P hat, the probability of success, essentially, which would be defined of the number of successes divided by the sample size. Yeah. Let's take a case where we have a P of 0.5. So for example, head or tail. If you take a coin and you toss it 20 times, we know we can calculate those probabilities from each single case with the help of the binomial table. As you know, the shape looks like a bell-shaped distribution, and we can use this little trick. We can essentially use the bell-shaped distribution function and approximate it to calculate to apply essentially sampling distribution on those cases as well. What we need for that are these formulas. The formula for the mean, which is sample size times the probability. So in this case, you toss the coin 20 times, n is 20. P is the probability of success. Let's say head is success, and success is, again, as I mentioned in the class, is not a value judgment. It's just a definition, a label that we give. So if I toss the coin 20 times, I know there's a 50% chance that I have head. The mean would be essentially 10 times. Now the variance is this formula that we use, n times p times 1 minus p. I mean, talk about that in the class too, so don't go too much in depth, but so we just need to plug in the values. N is 20, p is 0.5, so n times 0.5 times 1 minus 0.5. And then standard deviation, as always, is just the square root of the variance. So in this example, as I said, the mean would be n times p, so 20 times 0.5, 10. And our standard deviation would be, we just need to plug in those values, so 20 times 0.5 times 1 minus 1. And then the square root of that, so a standard deviation of 2.24, and that is describing it. So before we jump into approximation, we need to be aware that the approximation gives good results when we have two conditions met. One condition is that n times p must be greater than 5. In other words, the smaller p, the larger must be n. And then n times 1 minus p must also be greater than 5. So if p is very large, in that case also we need a larger sample size. So in other words, if we have an extreme value for the probability of success, so it's closer to 0 or closer to 100%, in those cases, we need to kind of compensate it with a larger sample size. If the p is close to 0.5, a sample size of 11, 12, something like that would be sufficient to get both of that larger than 5. So again, if p is close to 5, 0.5, close to 50% probability of success, the sample size of somewhat above 10 would be sufficient to fulfill both conditions. As p becomes smaller or larger, as it becomes more extreme, it doesn't matter in which direction, we would need to compensate it with a larger sample size so that both of these conditions are fulfilled. So that's something important to keep into consideration. And then we can use that approximation also to calculate the probability for one value, because as you know, for discrete probabilities, the probability, for continuous probabilities, the probability of having one value is close to 0. It's so small that we assume it to be 0. Here we know it is not continuous. Binomial distribution was a discrete distribution. So to calculate the probability for one value, we can use a little trick. So for example, let's say we want to calculate the probability of having 10 successes. If I toss the coin 20 times, what I can do is approximately, I need to just subtract 0.5 from 10 and add 0.5 to 10. So I can act as if it's like the probability of landing somewhere between 9.5 and 10.5, and that gives you the probability of 10. I do not face a problem anymore that to have the probability of 0, where we know the probability here cannot be 0 because it's not continuous, it's discrete. And then for other cases, so here, let's do the example. We know from the binomial formula that the probability of x being equal to 10 is 17.6%. If you do it with that approximation formula by inserting values of 9.5 and 10.5 and saying that it's the same as the probability of being between 9.5 and 10.5, but we get is 17.42%. As you see, it's not exactly that value, but we always say this is an approximation. So it is kind of close, and that works fine. Okay, so how can we now apply all that into the sampling distribution or the sample proportion? So again, we are now dealing with the sampling distribution. All we need to know are these formulas. So the variance of the sampling distribution of the sample proportion would be p times 1 minus p divided by n. Again, we have this phenomenon that as the sample size increases, the variance decreases, and accordingly also the standard deviation decreases. So just like before, with a larger sample size, what we observe is that the curve tends more into something like that. Right? So that's the effect of the larger sample size that we see here by having the n in the denominator. Okay, so here's an example that we can look into. We have a candidate whose popularity is at 52%. And we are taking a survey of 300 people and ask them if they would vote for him in the next election or not. We know that his popularity has not changed, so he has 52%. What are the chances that if we ask 300 people, at least half of them say that they are supporting that candidate? So knowing that his popularity is 52%, so our P probability for success is here 0.52. What are the chances that I take a sample size of 300, and out of those 300 people, 150 people or more would say that they are voting for him? Okay, so in order to calculate that, we need to first know what is our P that we are looking for. That's 0.5, and the P that we are looking for is 0.5 in our sample, but the P in the population is 0.52. Now, knowing that P is 0.52, what would be that as the standard deviation, all we need to do is plug in those 0.5 to the probability of success in the population, which is 0.52 times 1 is 0.52, and then what is our sample size? Our sample size is 300, so that's this effect again that we see here, right? And plugging in those values, calculating blah blah blah, what it gets us is a value of 0.0288. So 0.0288, that's our standard deviation. Now we have the mean of 0.52, we have the standard deviation of 0.288. All we need to do is figuring out the z-score. What are the chances that we have more than 50% of the votes in a sample size of 300? It's actually pretty much like the bottle example that we did, right? It was like the machine is filling 32.2 ounces. I took 4 bottles here. I'm asking 300 people, what are the chances that I have more than 32 ounces in the bottle? Here's the question, what are the chances that those 300 people, 50% of them will say that they support this candidate? So very, very similar. Again, I get a z-score. My z-score is minus 0.69. So I look it up, and the result should be 75.49%. So there's a 75.49% that at least half of the people will say that they will support that candidate. So this is it for chapter 8, and we will continue in the next video with chapter 9. Okay.